name is Peter Trampus. I'm a mechanical engineer and a university professor. At the same time, I'm Hungarian and still somehow active in my university, which is a small university in Hungary. But I'm involved in many domestic and international non-destructive testing, non-destructive evaluation associations. And so this is basically my the focus of my activity in the past decades. Anyway, I start the whole session will deal with the role and importance of non-destructive evaluation in the structural integrity assessment. And my presentation should be, I would say, introductory presentation. Why I can say, or I want to say, that the NDE is a foundation of the structural integrity assessment. That it's a vital part of the structural integrity assessment, and it will give you an overall summary of the NDT NDE. Let's go. So this is just to see that nothing will be moving or remains in the move, and nothing will operate safely without non-destructive testing. It's clear, I think, even if we don't think it every second or every minute in our life. So what is NDT? NDT, most of you, all of you know, but I put here the definition from the ASTM 1316 standard, just to be on the same platform. It's a development and application of methods, technical methods, to examine the materials or components in ways that do not impair the usefulness and the serviceability. And the goal is to detect, locate, measure, and evaluate flows, assess integrity, properties, composition, or to measure geometrical characteristics. Sometimes mainly we call it NDT, but sometimes we call it NDE, which is non-destructive examination. In some industry, non-destructive inspection, NDI. And I would like to point out that NDE later on in my presentation will mean non-destructive evaluation, which is an evolutionary phase of the non-destructive testing, not the same as the non-destructive examination. When was NDT born? This is a, I would say, not serious answer, but I can show you this picture that in the creation, the God was very happy that everything is very good. Of course, after a visual examination, which is a non-destructive testing method. And a more serious answer is that the wording, non-destructive testing, in this form appeared first ever in the technical literature in 1928, used by a US NDT actor, is Sperry, in context of magnetic testing. Magnetic testing was even before, but did not called non-destructive testing. And this picture tries to show that when the scientific knowledge basis was known, and when in the major NDT methods, and when the industrial application started. And you can see that except the acoustic emission testing and the penetrant, dye-penetrant testing, all the others, they were known long ago, but the others they also some 100 years or centuries before the industrial application started, and the industrial application started in the first half of the 20th century. In Germany, in the USA, in France, in Great Britain, and so on. What are the application areas, the major application areas? I said in the first slide or the second slide that everything is affected by the non-destructive testing, but the major application areas are the quality control of manufacturing, engineering structures, components, welded structures, bridges, machines, equipment. The other one is the examination of critical elements of the traffic and transport means during manufacturing and during the operation: cars, lorries, railway components, aeroplanes, ships, whatever. Also, energy, examination of the system structure components of the complex facilities providing energy for ensuring quality of life. The means of exploitation and transportation of the primary energy, the power plants, including nuclear, the distribution networks. The means of the medical diagnostics, means of scientific research, sport, entertainment, and I could continue further without dealing with the military applications. So it means it's a huge area. When I would like to be very simplified and general, I can say that the entity's overall goal is to detect the deviations from the condition which is suitable for use. And if we can also define two different aspects or objectives of the non-destructive testing. One is we can call social objective, which is to save the general public, the natural and built environment in case if a structure fails due to non-detection of a flow, which is basically the safety. The other one is the commercial objective, when we try to optimize the productivity of the assets which are inspected, and the productivity includes the service life and the performance of the assets or of the component of the machine. If we would like to classify the NDT, we can distinguish between two major types. One is the so-called quality control type NDT, it is a QC NDT, and the other one is the so-called fitness for service type NDT, FFS NDT. The quality control type is I don't want to degrade the meaning of the quality control type, that here the deviations expressed usually in analog signals, and these signals compared with artificial or reference signals, and the evaluation is made in this basis. And the closeness of this comparison depends on many, many factors. So there is this uncertainty in the evaluation. The registration or acceptance level depends on the testing methods. It's obviously different in the case of the ultrasonic testing and in the case of a magnetic or a visual testing. The other one, the FFS type, it's when we have to size the flow, which is usually expressed in the bounding rectangle or square of the flow. And then we use the analog signals only close to the registration level, and the sizing starts from here with special methods. This abbreviations here is typical ultrasonic testing abbreviations. This is reference response from the side rail holes or flat bottom holes. And let's move to the structural integrity area. What is the role of the NDT in the structural integrity assessment? The structural integrity, in my view, is a relatively new discipline which integrates many engineering areas. It basically refers to the safe operation of the engineering component structures and materials, refers to the residual life and how can it be achieved, which is a strong association with the life management aspects. The ASIS has a definition which is absolutely correct. Structural integrity, according to this definition, addresses the science and technology that is used to assess the margin between the safe operation and the failure. To be able to assess the structural integrity, we have to be aware of the following: the mechanical condition characterizing the operating loads and the environment, the structural materials properties, the initial properties, and their degradation in case of the usage or the application or operation. And of course, we need to know the existing flows, their position, and the characteristics. And this is the scheme which I think can illustrate this structural integrity assessment very clearly. There are three pillars, as I told. The first one is which I colored by green, is the loading and environment. I like to distinguish between loading, which are the pressure, the forces, the momentums, the mechanical loading, and environment, which includes the temperature, the humidity, the corrosive agent, the radiation, if any, and they all determine the component loading. The other pillar is the material properties, which are determined by the chemical composition, the manufacturing technology, the heat treatment, etc., of the engineering components and structures. And the third pillar is the flows. Here comes the NDE, the non-destructive evaluation, and I put here also in service inspection in the FFS type NDT. And this triangle is absolutely necessary to the structural integrity assessment. But important thing is that it is not a static situation. It's a continuously changing, it's a dynamic situation, because there are changes in the material properties due to the loading and environmental conditions. For instance, the embrittlement process, loss of toughness. And there is another changes. If there is a flow, it can propagate due to fatigue, due to corrosion, which means that these two processes, the changes in the material and changes in the flow size, which will lead to the decrease in the safety margin. And all this situation belongs to the structural integrity assessment, which can be deterministic, probabilistic. I don't go to the detail of this, but this is important, and the three pillars of the assessment scheme are equally important. That is again, illustration from the ASTM standard, because I realize many times not clear understanding of this wording like indication, flow, and defect. This is the scheme which starts with the non-destructive testing, and then depending on the method, which the indication can be something on the screen, an echo, some areas, some Lissajous curves, whatever, or can be something on the gray scale in a film or a digital detector array, it depending on the method. And the expert should first interpret the indication and select the real indication from the indications which we can call flow, because there are irrelevant indications and there are false indications. And if we have the real indication, if we are sure that the indication what we found it's a flow, then we have to evaluate. Evaluation is usually completed on the basis of standards, codes, or any other agreements, but basically standards where acceptance level are defined. And if the flow size exceeds the acceptance level, then it has to be rejected, and then it can be called defect. So in my understanding, flow and defect are different categories. Flow is an engineering category. Defect is a legal category, because it depends on the relevant standard. And some flows can be defects, and even the same flows are not defects in other application areas, because other standards are applied. Okay, just to see where we are. What is the role of the NDT? I think I can clearly state that NDT is not an end, but a means, where the end is the summary of the needs of the environment using the NDT, and the means the response of the NDT community to fulfill the needs. And if we go further in this line, then the needs analysis is that I put here a few major points, that it includes the increase of productivity, management of the aging assets, the spreading of the fracture mechanics, and the safety. Let's look at the productivity. I took an example from the car industry, where the target is to reduce the fuel consumption, so they reduce the weight, they apply novel materials, they apply high strength, low alloy steels, whatever, and it has a serious consequence on the non-destructive testing, because it gives increased requirements, and the use of novel materials, which are the composites, the ceramics, the light metal alloys, they define new NDT task. The second need is the management of aging assets, and my example is from the nuclear power plants operation. In this diagram, you can see the ages of the operating 440 something nuclear units in the world. And you can see that the peak is somewhere here in the 30s to 35th year. So the nuclear fleet of the world is quite old. And that's why, and other political aspects of the nuclear application, the value of the operating plants are high. And that is the reason that life management and operating life extension of the nuclear power plants are on the agenda. And it means that we need a serious aging management system in the aging nuclear power plants. And the consequence of this is that the role of the non-destructive testing becomes more and more important. This is just as an illustration how the NDT can contribute to the service life estimation reliability. In this diagram, you can see in the horizontal axis is the operating time, the years, and in the vertical axle, you can see a loading parameter on the material parameter or material characteristics, which resist the loading. And if we just assume that the loading is constant, so we don't operate the power, whatever, and the material parameter is continuously decreasing as a consequence of the aging. And there is an initial safety margin, and there is a final safety margin, which is necessary in case of the nuclear plants. And the crossing of this material parameter with this safety margin level determines the service life. Sorry. And if we want to reduce the scatter of this aging process, we need examination methods, we need evaluation methods, we need model building. So this is the room for improve the estimation reliability, and it can result in the increase in the service life if we have this target in our nuclear plant. It is just an illustration, and you can just look at the amounts, how many millions of US dollars cost these aging-related degradations in different nuclear power plant components. Okay, third one is the fracture mechanics, and it is very strongly related to our today's session. It led to a dramatic changes in the design concept and in the operation concept of the engineering components. And the consequence, I will tell you in the next slide what damage tolerance method and fitness for service means. But the consequence for the NDT is, or was, that the NDT capability has to be characterized in a quantitative way. This is an example from the world's leading boiler and pressure vessel code, which is the ASME code. And the section 3 is the construction code for nuclear plants. And the section 11 is the in-service inspection code for nuclear facilities or nuclear components. And you can see that here is the form factor of here is a surface flow, and here is the depth of this flow, which is, in this case, it is the force of the wall thickness, and there is a 10 safety factor, and this is valid for the design, and this is valid for the operation. And perhaps this table shows very important information and the differences between the pre-fracture mechanics concepts in the design and in the inspection or testing. And we called it a safe life design concept, which we call today damage tolerant concept. And I don't want to show all the boxes, but let's see the structural integrity. In the past, our assumption was a defect-free or flow-free structure. And in the damage-tolerant structure, which is a calculated critical initial flow size and the growth of the flow. So two different concepts. And if we come back to this, you can see that in the design, the designer calculates this 1/4 of the wall thickness flow and justifies the applicability of its components. In the NDT NDA acceptance criteria, in the safe life concept, we always told that no flows. This is a flow free. And in the damage tolerant structures, we can live with the flows, but we have to know the flow type, the flow size, the location, the orientation, nearest neighbor, whatever. So it means that the NDT methods, techniques, whatever, they have to be able to deliver all this information. And NDE procedures. It's very important. Maybe later on, I think in our last presentation, we'll deal with this aspect that in the past we had prescriptive NDT procedures, and now we have validated procedures, and which are characterized by the applicability, reproducibility, capability, repeatability of the inspection. And the fourth one is the relation attitude to the safety. I think this is a general process that the risk accepted by the society is decreasing. And at the same time, and as a consequence of this, the safety regulations became progressively more serious. And that is one reason that the risk as a tool, risk considerations appear in the assessment. And the consequence of this, that the NDT efforts focus on the higher risk areas, which could result in the NDT volume reduction. But sometimes the conventional NDT procedures and equipment are not good enough. So the risk-informed inspection brings new requirement to the NDT. And quickly, because the time is running, the NDT responses, how the NDT community responded or is responding to all these needs. I would say quantitative NDT, the information technology, the modeling, simulation, new techniques, novel methods. This is the basis of the quantitative NDT, which the major information or the major tool is the probability of detection, the POD, which will be a separate presentation on this. So I don't want to the details of this, but just to see what probability of detection is, it's a number, the fraction of detected flows in the total number of all flows as a function of flow size. And in this picture, this is the probability Excel, and this is the flow size or relative size. In this diagram, it is a concrete flow size, and this brown curve is the probability of detection, which you can see that in the smaller flow sizes are lower and go back, and then let's say here we achieve the 95% probability in the case of the 3.5 millimeter, and this is the scatter here. Later on, we will come back to this POD in the last presentation. This is how the NDT formulated or went to the NDE. In the pioneer period, in the past, we called it non-destructive testing, or we still call it non-destructive testing. I told you before, it's a quality control tool. The overriding role of the standards were typical. The usual results were allowable, not allowable. And there was a very strong dependence on the human factor, and even these weaknesses, it was accepted because there was a substantial design margins. And the recent past and present, I mean decades, non-destructive evaluation, where quantitative requirements is the quantitative non-destructive evaluation, led to the changes in the design concept. I explained why could it be go into this direction, because there was an enormous development in the fatigue and fracture theory, the risk analysis, the condition monitoring, the life management. And now today, tomorrow, in the future, we move to the high tech, from the human computer to the computer environment world. Information technology, micro nanoelectronics, without details. What happens in the world? Extreme rapid development. Different integration of different technologies. Dividing line between software hardware becomes indistinct. Effects of quantum physics are possible to measure. Increase of sensitivity. Instead of detecting flow, proactive management of materials degradation comes into the picture. In the production, it means a real-time automated inspection. In the operation, it's an online monitoring. Structural health monitoring, modeling simulation, 3D visualization, deep machine learning. So many things which clear and direct consequences of the development in the information technology, micro and nanoelectronics. I have a few examples, but I jump this because I will run out from the time. I uploaded my presentation. You can see this. They are all demonstrated that what was the consequence of this enormous development. That is also some technical development in the equipment technique. Just stop a bit in the deep machine learning, which has many aspects and many possible areas. What we need to have this deep machine learning, we need a processing power, we need algorithms, and we need data. And this could have some place in the non-destructive testing area too. And this is the proactive management of materials degradation, which means that this is the structural integrity limit, this is the NDT sensitivity limit, and today, and maybe in the yesterday and today, we concentrated the existing crack size, but in the future we try to concentrate not to the flows, but to the areas where flows will be developed. And it is very important. So proactive management of materials degradation. One method is the metal magnetic memory method. I mentioned the modeling and simulation. It is the ultrasonic testing. We need to distinguish between modeling and simulation. Modeling limits mainly to the sunbeam area, and the simulation also includes the flow response. There are a couple of softwares worldwide used for this, and it is really I called it the designer's virtual examination, which we can use in the application in the phased array. Next presentation will take in the flexible phased array, the personnel training, the entity system qualification, and so on. New NDT techniques. Again, some of them will be later in separate presentations. In the UT, electromagnetic acoustic tensor, in the radiography, the computed radiography, the digital detector array, they also revolutionary development in the radiography. I don't deal with phased array because Raphael will continue with this area, and this is just an example how the conventional ultrasonic testing measure a flow, a corrosion crack, only 35 millimeter, and the phased array technique is a dissimilar metal weld. It measures the real size, which is 49 millimeters. So this is the capability of the phased array compared with the conventional UT. And the phased array has other consequences, the full matrix capture and the total focusing method, which utilize the given characteristics of these techniques. The guided wave or long-range ultrasonic testing is also a technique which is able to inspect usually long components like tubes, pipelines, railways, and the ultrasonic wave goes in the whole cross section and can cover hundreds of meters of the components. The novel methods, just to mention, the nonlinear acoustics, the terahertz, the laser techniques, dynamic thermography, again a separate presentation we will have, MMM method, a separate presentation should have been done on the robotics and the non-destructive testing, where the drones and other robotics are playing a leading role. And finally, just a word about the NDT 4.0. You know, Industry 4.0 is a concept now. It's a merging the virtual and the technical engineering area, and just taking into consideration the Industry 4.0, the non-destructive testing started to position itself in this new world. And there is one concept of the NDT 4.0 is not necessarily the only one, but it is one. I feel it is feasible and credible, where the NDT 0.0 is the use of the human senses, which is the origin of the NDT. 1.0 is to enhance the human senses with tools, which is the visual testing, penetrant testing. 2.0 is the extended sensing, when we look into the component. That is the magnetic, eddy current, ultrasonic radiography. The 3.0 is the mechanization, automation, reconstruction. It is the computer tomography, total focusing method in the phased array. And 4.0 is just basically the concept of digitalization, the cross-linking, networking, all of this, and no need for the 3.0. Can 4.0 even applicable for the manual NDT, and it can synchronize with, can lead to the synchronization with the Industry 4.0, because I'm a little bit, I'm not little bit, I'm an NDT fanatic, that NDT is one of the biggest data source for the Industry 4.0. And finally, my summary, that we went through on the, and I explained to you the structural integrity assessment scheme, the role of the NDT, the NDT-ND differences, the needs for the NDT and the responses of the NDT community. And I close my presentation that the changes in the world and the changes in the NDT techniques is dramatic, but one thing does not change is the physical basis of the NDT methods, and the NDT method is not up to date just because it is digitized. But it is if we know its limitation and capabilities. Thank you very much for your attention.